Before I continue with this, we need to remember that OpAmp is not just a differential amplifier. Apart from that, there are other parts to it, right? So we are actually, since differential amplifier forms a very important part of the OpAmp, so we are just trying to learn this a bit more. Okay, so a differential amplifier usually looks like this, and it is basically coupled with other kind of amplifiers, okay, and devices within the OpAmp. So it's basically an IC, it's an integrated circuit, and one of the part of the integrated circuit is the differential amplifier. So you know what happens usually in a differential amplifier, we basically have got two transistors, okay, which are actually coupled together, and they are coupled without using any kind of capacitors or any other resistors or something like that. Okay, it's directly coupled capacitor. No, sorry, directly coupled transistor. And what we see is we basically have got two regions where we can get the input. So we can give an input on this end, or we can give an input at this end, and we can obtain the output from here or here. Okay. And if we take the input from this end, then what happens is you can actually have basic input at this particular point. Okay. And this will actually result in an input signal through this emitter terminal in the second transistor, that's Q2. And finally we actually going to have output, right? So in case we are having an input on this end, we're going to get an output in phase on the other end. On the other hand, if you are having an input on this end, and if you want to take the output from this output, we are going to have it at out of phase 180 degree. What we did not do the other day was we actually tried to understand it, but we have not written anything based on the operation. Okay, so we're just going to write down a few points on operation, and this is the symbol of differential amplifier in general. Okay, so please remember, differential amplifier and OpAmp are two separate things. Okay, differential amplifier is a part of OpAmp. Okay, so it's not that the OpAmp entirely is just like a differential amplifier. That's not true. So what we're going to look into is operation. Okay, and I will just concentrate on a single ended input. So we're just going to look into the operation of a single ended input of a differential amplifier. Okay, so let's say, let me just take an example. I'm applying a signal to, let's say, input 2. Okay, to input 2. This diagram is only for reference, so you can understand this. So let's say I'm applying a signal to input 1. Okay, so that is, sorry. So that is basically nothing but base of Q1. Okay, so that's base of Q1. So you are going to apply a signal to the base of Q1. So if I just rub off whatever we have it on this side, okay, maybe, and I will just rub this part off. Okay, and what we have is this is base of Q1, and we are going to apply a signal at this particular end. Okay, so what I'm saying here is that I'm taking the first case scenario that we have seen the other day. So we are going to apply an input here, and then what we are going to get is here we are going to get a signal, and this won't be much amplified. Okay, and then finally when this signal is fed into this part, okay, we are going to get a signal will be totally in phase and amplified on the other end. Okay, and if you want to take the result on this end, okay, on this end what is going to happen is we are going to get a, if we're going to take it on this end, we are going to get it out of phase. Okay, this is going to be out of phase by 180 degree. So this is how exactly a signal is getting amplified. Okay, so based on this image we are trying to explain the facts here. Okay? So what I'm saying is we are applying a signal to input 1, that is base of Q1. Okay, and we can say that base of input 2, okay, that is base of Q2, right? So base of Q2 is grounded. So we are having the base of 2 as grounded. Okay, so that means that we are not going to apply any kind of signal here. This is basically going to get grounded. Okay, and we are just going to apply a signal at this particular end. Okay, so let's ground this. So we'll just directly connect it here. Okay, so just using a different color so that we can easily understand this, right? And this is the signal that we are applying on this particular end. Okay, so this is the correct circuit diagram to do the explanation as per whatever I'm defining now. Okay, so then what happens is, since when you write down in your exam, you can write it down in your own words, but try to make it concise and to the point. Since the emitters of Q1 and Q2 are common, so you see emitters of Q1 and Q2 are common. We have the emitter here and we have the emitter here, so both of them are connected, so they are basically common. Okay, so what we can say is that emitter signal, okay, becomes input to Q2, right? So what you see is, since they are common and you get whatever signal from this end, this will be actually an input to this Q2. Okay, so this will be basically acting like a common emitter configuration, right? So what happens is, the signal in Q2, this is exactly what I said, the signal on the emitter Q2, okay, will be amplified, right? So this is getting amplified and appear on the output of Q2, right? Output of Q2. Okay, so this output of Q2 is basically nothing but collector of Q2. If you just look into this, collector of Q2. So this is the first part of the operation, and if you want to get an amplified signal, this is something what you're going to get. Okay, and this is important because, you know, when we study transistor, we know that if we are actually using a common emitter configuration, there is a phase reversal. Okay, so when we basically, what we do here is, usually when output is taken, okay, at 1, okay, we're basically taking the output at 1. So basically we are talking about this particular part. Okay, what we have here is, it is a CE config. Okay, so if there is a CE config, there is phase reversal. So if there is a common emitter configuration, we will actually be getting a phase reversal kind of scenario. Okay, so how do you understand that this is a phase reversal, and why we say it's a common emitter configuration? Because you see, you are going to take the output from this end. Okay, now this particular end is common to both input and output. So you see, the common to input, this is input, so this is your input, and this is the part where we are taking the output. So this is the output part. Okay, and this is the output, and both the sides we have emitter is common. So that means we are calling it to be a common emitter configuration. So if it's a common emitter configuration, there is always a phase reversal of 180 degree. Okay, on the other hand, when the output is at 2, okay, or what we can do is, we can just take it in separate way, is, let's say when the output is taken at x, okay, I'll give you what is x, the signal is having almost the same amplitude, So what is this x here? X, by x I mean this particular point. Okay, so let me just mark this as x. So it's almost the same. Okay, because there are some kind of signal losses, so sometimes the amplification might be a bit lower, but then it is almost the same, the amplitude, and it is not yet amplified. Okay, and what happens is, so if I'm just writing down this down in general, okay, so from Q2 we have the base grounded, right? So we can see that the base is grounded in this particular part. The base is grounded in this Q2. Okay, and signal is applied from the emitter base, from the emitter side, sorry, not emitter base, emitter side. So what we have here is, we're basically applying the signal from the emitter side. Okay, so this is basically nothing but acting like a common base configuration. Okay, So in if you just talk about a common base configuration, you are going to get no kind of signal reversal. There is no phase reversal. Okay, so this output is having no, okay, let me write down this no in general, phase reversal. Okay, so there is no phase reversal. Okay, so this is what is done when we are considering this end, and you can actually observe a similar behavior when we are actually giving an input at this particular end. Okay, so if we take it at this particular end, we are also going to have a similar behavior. Okay, and this output, that means we basically can, sorry, we can consider it to be the common base configuration. Now you'll say why it is common base, because you see here, this is your base, right? This is your base here. We have the base at this particular point, and you're going to get the output at this particular end, right? And the input at this particular end, okay, where the base is again common. Okay, so the input is across the base. Okay, you have it across this base emitter, okay, at this particular end, and then the collector base will give you the output. So you basically can consider it to be a common base configuration. Now if you get back into transistors, we know that in common base configuration there is no phase reversal, so you get this. And if we talk about common emitter configuration, there is phase reversal, so we get this. Okay, this is also a kind of question which usually comes in exam, but that is the question which is not based on this but based on transistor unit. Okay, so this question might be there. Okay, so that's it for differential amplifier. Okay, now what we are going to do is we are going to just look into more details of an op-amp. Okay, so as I have already told you about op-amp, okay, we have studied already a bit about op-amp now. So what I'd like to start with is some more basics of op-amp. Okay, so in op-amp what usually happens is that the first thing is the symbol, and I think we already have understood the symbols, right? So since we are starting again with the op-amp basics here, okay, but we are going to just look into some more parameters here. Okay, so if you look into this differential amplifier, we know that there are two input voltages that are need to be supplied. Okay, and so this is, let's say this part is plus V and this part is minus V. Okay, and then we actually say that this end we are going to get the output. So this is your output, right? And this is your inverting terminal, this is your non-inverting terminal. Okay, and then we can just represent this as V2, and this one can be represented as V1. But please remember that this minus and plus which is written here does not signify the polarity. It only signifies it's an inverting terminal, it's a non-inverting terminal. In simple words, if I am applying a signal through this end, we are going to get a phase reversal. If we are applying a signal through this end, we are going to get the signal in the same phase. Okay, so this is what you have to remember. So this is a symbol which is generally used, but we can drop this plus V and minus V sign. Okay, so in general, when the op-amp symbol is used, we are usually using this. So don't get confused. If someone is using this symbol or this symbol, both actually represents an op-amp. Okay, so that's there. So let's just look into some important points in op-amp. Okay, so maybe we can start with the output voltage from op-amp. Okay, so the first topic, that first parameter that we can actually talk about is output voltage from op-amp. When you write down op-amp, please write down O and P in capital, A in capital, and then A and P can be done. Okay, so output voltage, okay, which is the most important parameter, because the aim is to actually amplify a signal. So we want to amplify the output voltage. So we need to know what are the factors on which it depends on. Okay, it basically depends. First thing is voltage gain of op-amp. So what is the voltage gain? Whatever is the voltage gain multiplied by the input voltage difference, you will be basically getting that as the output voltage. So even if you have a very small of voltage of 1 millivolt, okay, a good device will basically give you a very high voltage output. That is also one of the advantages of OpAmp. Okay. Next, polarity. Okay, relationship between V1 and V2. Okay, this is quite obvious. Polarity relationship. But if there is a phase reversal, if there is no phase reversal, if you are considering a signal only through V2 and you are not considering anything through V1 you can keep it grounded and so on. Okay, so this relationship also will decide what will be the output voltage, and of course the supply voltage plus V and minus V. So these are the factors on which the output voltage of our OpAmp depends. Okay, and since we are talking about output voltage, I think we should talk about something which we call as the voltage gain. So how much is the voltage gain, okay, of OpAmp? Okay, so I think this is quite obvious. So maximum possible gain, okay, from an OpAmp is called open loop. So there is an important term here, open loop and closed loop. We're just going to look into that. Open loop voltage gain, okay, and denoted by A to the base OL. Okay, so I'll just write down that. And this A to the base OL is usually 10,000. What exactly do you mean by open loop? Open loop means that we are actually not going to apply any kind of input, okay, feedback. We are not going to apply any kind of feedback into this. Okay, so maybe I can write down this here. Open. I'll explain this with the help of a diagram. It'll be more clear. If you just write down include open loop, no feedback path, okay, from output to input, okay, of OpAmp, input of. So before I explain this, let me just complete this here. So basically just write it down as AOL, open loop, okay, AOL, open loop. So if you just look into this particular circuit, this is a kind of open loop circuit, okay. So that means if it's an open loop, we also should have something which we call as a closed loop, okay. So let's just draw that closed loop circuit, and then you can easily differentiate between open loop and closed loop. So closed loop circuit is also quite used, okay, it's quite popular. So what we do usually is we'll just draw this circuit first, okay, and let me just keep on one end, okay. So I will draw some resistors at this end, okay, and then I can have a signal at this particular end, and then I can ground it. And let's say this is the non-inverting terminal, and let me say I'm grounding the non-inverting terminal. Please remember, if I'm grounding one terminal, that means I'm just using a single ended input, okay. So that is there, okay. And then what happens is a little bit of output I'm considering, and I'm feeding it back into the input, okay. I'm feeding it back, so please remember this term. So this is basically nothing but a closed loop, okay. So it's a closed loop gain. So let me just complete this figure, okay. So what we have is we can actually have an output across these two ends, okay. So the output will be across this end, okay, and then we are actually having a feedback resistor connected here, okay. And let me just write it down as RF. So F basically stands for feedback, okay. And then you basically have here an input resistance Ri, okay. And then we have got, let's say, the voltage V2, okay. So this is V2 because this is the inverting terminal, and the non-inverting terminal I'm usually representing it by V1. You can just refer to this figure, okay. So this is V1. So V1, there is no input, this is 0, and we are having a signal at this particular input, okay. So this is basically nothing but a closed loop, okay. So if we just want to level this figure. Okay, this is an example of closed. Okay, so a closed loop is something like this. So you understand now what is an open loop is all about. Okay? So maybe I can just write down a few points here. So this is for a closed loop gain. Okay, so what happens is when a feedback path is present, path is present. Okay, the resultant circuit gain is closed loop voltage gain. So what happens usually is nothing but you are actually applying a feedback to the circuit. So there are devices where you actually in fact apply a feedback to the circuit. Then the power or the energy needed to keep the circuit moving or driving the circuit is much less. Okay. So this is actually an advantage of having a closed loop circuit. So this is basically called a closed loop circuit. So might be we can just write it as CL. Okay. So we'll just write it down as CL, closed loop. Okay. So this is what is the op-amps connections are all about. Okay. So this is a closed loop, this is an open loop, and we need to just kind of remember these factors. Now what we are going to look into is something which we call as a practical op-amp. So op-amp can be practical in the sense that we basically need some parameters which needs to be optimized, okay, so that it can actually give you the desired output, and that is what is the use of a practical op-amp is. Okay, so just write down few points here. I'm not going to write down long sentences, but I think I'll just give you the important points here. So practical op-amp, the very first point that we should note is it should have a very high voltage gain. I think that is quite obvious because the ultimate aim is to increase the voltage. Okay, so basically a small V in, right, a small input voltage, okay, will produce large V out, right? So if you basically have a very small input voltage, you're going to get a very large voltage output. Okay, and that is why you actually need a high voltage gain. So that is there. So practically that should be there. Point number two might be very high input impedance, very high input impedance. So you really don't want to amplify the current, you need to amplify the voltage. So for that reason, you have a very high input impedance. So I hope all of you know what is impedance, right? You basically have this as a resistive property of any circuit. It might have inductor, capacitor, okay? Basically that is called impedance, okay? And that resistive property towards current is something which we term as impedance, mostly used in an AC circuit, okay? So for very small input current, we don't need the current high, so we're just going to have a very small input current. So if the input impedance is very high, you're not going to have any kind of current input into the system. And then finally, very low output impedance. So output impedance should be low. So please don't mix up these things in your exam or quiz. Okay, so just remember this. So if the output impedance is low, you understand that the output voltage, okay, output voltage is independent of output voltage is independent of the load connected to op. So if the output impedance is low, in general it means that we can just go back to the previous page. If the output impedance is low, that means this part, if the impedance is low, whatever is basically say output impedance, the load connected, so this output is independent of the load connected, so this output voltage whatever you have should not be affected by the load. Okay, but if this load is very high, this output impedance is going to be affected. Okay, because resistance or impedance whatever, it plays a very important role. but we don't want that. So this output impedance should be minimum, it should be very small. Okay, so that is why it is given. So you know, both the resistances which we connected, the input and the output, has a very important part to play. So that is actually a practical op-amp. Okay, what about an ideal op-amp? Ideal op-amp is obviously everything should be very high or very low, right? So in general, if we just consider an ideal op-amp, okay, if we consider an ideal op-amp, this impedance that we are considering, that is the input impedance. Let me write it down as this. Okay, and so this input impedance that we are considering should be infinity. So it says it's very high. Okay, so this input impedance is this Z in. Okay, this is output impedance Z out. Okay, so this should be high, very high. Okay, on the other hand, if you're just considering the voltage gain, okay, so this can be considered as the voltage gain. Let me denote it as AV. Usually it's denoted with AV. This should be again infinity, very high. Okay, and the third case is you are going to have the Z output, and output impedance will be 0. So you know, if you think about it practically, you cannot have an infinite input impedance, you cannot have an zero output impedance. There will be some impedance, no doubt, even if it's somewhere which is connected. A voltage gain of infinity is very difficult to achieve. Okay, you cannot have that much of gain. Okay, so based on this, we can say this is the case for an ideal op-amp, and this is the case for a practical op-amp. Okay? And this is what is important in this particular case. Okay, now there are certain terms that we should know. Okay, and I think one of the term which is important is bandwidth, if you remember. So all of us remember what is bandwidth. You know, certain devices will actually work well within a certain frequency range. Okay, and this is something which we call as the bandwidth. The range within which it works the best or optimum, that is bandwidth. And bandwidth is not something which is maximum. Okay, it is basically having a very short range, so it is important. Okay, so bandwidth is the limited range of frequencies. So just going by a definition within which an electronic device works. Electronic device works. So if you say that FM radio, okay, or an AM radio, okay, analog modulation or frequency modulation radio, they will work within certain range. So analog modulation basically doesn't deal with frequency, but if you talk about an FM radio, the word bandwidth has a meaning. Within what range it works. So if you take up any kind of channel, let's say 94.5 FM, we can get some signal at 94 also. You can get some signal at 95 also. So this width is very less. Okay, so it's very within a very short range. Okay, that it is working. So that is basically the bandwidth of that particular channel. Okay, and if you connect with this, we actually have got something which is a technical term. It is basically called as gain bandwidth product. Bandwidth product. Okay, so this is GBP, gain bandwidth product. So this is a term, and I think we can just write it down as there. Okay, so this gain bandwidth is given as A to the base CL. CL is closed loop. Okay, into F2. Okay, I'll tell you what is F2. So that means the frequency which is being applied is basically nothing but equal to F of unity. Okay, so before I write down what are these, let me just fill it up. So this is closed loop gain. This is the applied frequency. Okay, and this is equal to unity. This is the general formula for this. Okay, and what are these terms here basically? Okay, so this ACL. Okay, ACL. ACL is basically, you can understand this. This is the closed loop gain, right? So this is the closed loop gain at frequency F2. So please understand this, that we are basically talking more or less about an AC circuit. So the frequency plays a very important role. Whatever is the gain of the circuit will actually depend on what is the frequency of the input signal. Okay, so at frequency f2, so that's the closed loop gain. And if we just write down what is f unity, okay, that is the frequency at which, okay, frequency at which this closed loop gain, okay, that means ACL is equal to unity or 1. So the frequency at which the closed loop gain is 1 is basically called as the F unity. Okay, so if you just take this gain bandwidth product, you are going to get this term. So this is basically nothing but a measure of the bandwidth based on the frequency. Okay, and of course, depending on what kind of op-amp you are using, you will be actually getting a particular closed loop gain, and based on this we can actually have this bandwidth. So why this is important? Because there are numerical problems which is coming in this particular unit, and this might be based on this particular formula. Okay, nevertheless, next day we might actually practice a few numerical problems for this. Okay, one more term that we should know is called the slew rate. Okay, SLEW. So SLEW, slew rate. And what exactly is slew rate? It's basically a measure. So the output voltage will change, right? You apply an input signal and output voltage will keep on changing. So how fast this output volt changes based on the input signal is something which is called a slew rate in general. Okay, so it's basically a measure of how fast the output voltage can change. Okay, and this is very fast. Okay, what happens usually is it is usually measured in volt per microsecond. Okay, volt per microsecond. So per microsecond, how much is the voltage changing? So in a typical device, the slew rate might be 0.5 volt per microsecond. Okay, so that is there. So I can just take an example, maybe 0.5 volt per microsecond. So that means in every microsecond, 10 to the power minus 6 second, there is going to be a change of 0.5 volt. Okay, and that is what is basically called as the slew rate. Okay, so if we just want to find out the frequency, maximum operating frequency, so every op-amp will basically work at a certain frequency range, and if we actually want to find out what is the maximum operating frequency, we can use this relation of slew rate. Okay, operating frequency. Okay, so this maximum operating frequency, you can write it down as F max. Okay, and this F max is equal to slew rate, okay, divided by 2 pi V Pk. Okay, and what is Vpk? So you're basically going to have output voltage, and what is the maximum output voltage that you are getting is it called the Vpk. Okay, so the peak, okay, that's Pk, output voltage. So this is one more formula that you should know. Okay, if you want to find out maximum operating frequency of an op-amp, you should know slew rate. So slew rate, that means that how fast the output voltage can change, and once you get that, you should also know what is the maximum output voltage, and based on this you can actually do your calculation.